Okay, in the last part of the class, we talked about two rules, the sum and the product rule. So let's see how these sum and product rules actually come. Rule where we said, if there are T1 of n plus T2 of n, and these have time complexities, this is max of order of f of n, comma, order of g of n. And what do these correspond to? This T1 of n is like, I have one program P1 here, another program P2, and I'm talking about running these two programs in sequence. P1 has a time complexity of order of f of n. P2 has a time complexity of order of g of n. Then what this rule says is that the time complexity of the combined program P is going to be the max of order of f of n, comma, g of n. This is what it tells us, okay? And we also saw something called a product rule. And let's see what this product rule is all about. It says if T1 of n star T2 of n equals O of f of n star g of n. What is the meaning of this? It's like this. I have a while something, let us say, condition, do the sequence of statements here, and I have a end while. So this, for example, this statement together with this corresponds to the loop. This corresponds to the program P1 here, and let us say these two statements constitute the program P2. What does it mean? This program P1 is executed P2 times, and that is why the time complexity is the product of the time complexities of the individual programs. We say that if T of n is some is a polynomial like some n to the power of some x, then we say T of n is theta of n to the power of x. Okay, this is one more rule that we have on. We call this rule 2. There's another rule 3 which states that if I have log k to the n for some constant k, this is big O of n for any constant k. What does this mean? This essentially tells us that logarithms grow very slowly, okay? So we can summarize the properties of complexities of algorithms, and let me leave it incomplete. So I have a function here and a name for it. If it takes a constant among constant units of time c, we call it constant, and we generally represent it by O of 1, omega of 1, depending upon whatever bound we are using, theta of 1, okay? And this follows for every one of them. If I have log n, we say it has logarithmic complexity, and therefore this would be O of log of n, and so on. Log squared of n, again this is log square, and you will write this as O of log squared of n, and so on. If it is n, this becomes linear, and we write this as O of n and so on. N log n, this is order of n log n. There's no specific name for this. And n squared, we will say it's quadratic in the size of the input. Order of n squared, n cubed, cubic, order of n cubed, and so on. We have similar things for the theta and if it is the order of 2 to the n, then we call this exponential, and we will see this is a very serious thing. It's very easily possible without, if you're not careful, to get exponential type complexities. Next, we'll look at the proof of T1 of n plus T2 of n equals max of O of f of n comma O of g of n. Let's see how we get this. So T1 is the time complexity for program P1. T2 is the time complexity for program P2. And what is this? These are two programs to recall, P1, P2 like this. Okay. So now we have T1 less than or equal to C1 Fn. That's what it tells us. N greater than or equal to N1. T2 less than or equal to C2 F of n, n greater than or equal to N2. Okay. Now, let N0 be equal to max of N1 comma N2. Then T1 of n is less than or equal to C1 F of n, n greater than or equal to N0, T2 of n less than or equal to C2 G of n, n greater than or equal to N0. Okay. Because both n, n1 and n2 are also positive. Now let us have C3 equal to max of C1 comma C2. Now we can easily say T1 of n less than or equal to C3 Fn, T2 of n less than or equal to C3 G of n. And when I look at T1 of n plus T2 of n, I can say less than or equal to 2C3 max of f of n comma, sorry, max of f of n comma g of n. Okay, so this should not be here. N comma g of n. Can easily write this. So this becomes T1 of n plus T2 of n is less than or equal to some constant c max of f of n comma g of n, which is less than or equal to big O of max of O of f of n comma O of g of n. That is what it tells us. Okay. And this is a simple program that we have here. And why is this important? Let us look at this. We never write T of n is, we don't write it as order of 2n squared or order of n squared plus n. Why? Because it is always possible to find a C, comma, n naught such that T of n equal to O of n squared. Let me, because this is 2 over here, I can, instead of 2, I can have any constant which is large. That is very easy for the first part. Let's look at n squared and n. N squared grows much faster than n, right? So if n tends to infinity, that's what we're looking at, because we're looking at asymptotic bounds here. N tends to infinity, then n will grow much slower, and it doesn't dominate the computation. Okay, that's what we are looking at. And to find relative growth of functions, we can use L'Hospital's rule if necessary. What we do is we compute the ratio of the two functions. We find limit of n tending to infinity, f of n by g of n, and if the limit of n tending to infinity, f of n equals infinity, and the limit of n tending to infinity, g of n is also infinity, then all that we do is, as in this particular case, you take n squared tends to infinity and n tends to infinity as n tends to infinity. So what we do is we take n squared by n, then we take the derivative of this. So what we do is, applying L'Hospital's rule, we say that limit of f of n by g of n, n tending to infinity, equals limit of f prime of n by g prime of n, n tending to infinity. So if I do this particular example, so you get 2n by 1 over here, and clearly n tends to infinity. F of n grows much faster than g of n. So this is how you prove these asymptotic bounds. Now, what we'll do is, we saw this for the, let's take one example now, where we have all these sum rule and the product rule which come into play. Let's say I am writing a program so let us say I'm writing a program, sum, like this. I have two variables, sum and I, which are 0. And let's say n is some integer which is greater than or equal to 0. Let's see, this is my precondition before I enter the loop. While I less than n, do sum is assigned the value of sum plus I. I is assigned the value of I plus 1. Let me make it less than or equal to because I'm adding 0 to end Y. Okay, so this is like this part is the program P1 and this while end while is your program P2. So you have a pre-program P1 which runs inside P2. So now what is interesting is we see that means P1 is going to be run P2 times, whatever it is. It's a product of, this is what we mean by the product rule here. So now let us look at a time complexity of P1 here. This is going to be order 1 because there's an addition here, another increment over here. We assume that all these take constant amount of time. Whereas the while block has a comparison here, and this is being run some n times. Each comparison operation, let's say, takes a constant amount of time. So the program P2 takes order n time. Therefore, the time complexity of T1 is T1 of n is order of 1. T2 of n is order of n, and the time complexity of T1 of n into T2 of n is order of n into 1, which is order of n. Okay, so I think we can stop here for today. And so we talked about 2 examples. Which used the sum rule and the product rule. We'll look at some more examples now. Let us see what will be less than n to I is assigned the value of 2 star I. What is the time complexity of this loop is what we want to find out. Now, again, we have a program P1 here, another program P2 here. This one is a simple assignment statement. Therefore, its time complexity is order 1. And this one, how long will it? Let's say I start with I equal to 1. Then what happens? And let's say n is 20, something like that. I takes values 1. Then it takes 2, 4, 8, and 60. Okay. So instead of running 20 times, it only runs 5 times. Let's say n is equal to 8. How many times does it run? 1, 2, and 4. Okay. N equal to 16 runs 1, 2, 4, and 8. So if you want to characterize it in terms of n, which is the input, so can you guess what will it be for n equal to 32? It will be 1, 2, 4, 8, 16, 5 times. So it's like log of 16 to the base 2 or log of 32 to the base 2 and so on. So the time complexity, so what does it mean? P2 runs log of n to the base 2 times. P1, the cost of this is order 1. So this order of log n. And P1 runs within P2, therefore the overall time complexity is T1 star T2 of n equal to O of log of n to the base 2 into 1, which gives you big O of log of n to the base 2. Okay, so this is the time complexity of this particular program. And next topic that I want to talk about is recursive functions. What happens in recursive functions? Okay, how do we write the time complexity for recursive functions? So let's take some examples here. Let's do the sum using recursion. And I can write a function module. Let me call it sum of n and takes as an argument int n if n equals 0, return 0, else return n plus sum of n minus 1. So this is what we will be. So of course we assume in all these examples that I didn't write the precondition everywhere. N is greater than or equal to 0. Okay. How do we analyze the time complexity of this? Let us take n is greater than 0. Let's say it is t of n. If you look at it for the nth loop, for example, there is some constant operation. N equal to 0, there's one operation. Let me say that the cost of this operation is C and the cost of this operation is D altogether. Okay. So T of n, we can write it as C plus T of n minus 1. And T of n minus 1 equals C plus T of n minus 2, T of n minus 2, C plus T of n minus 3, and so on. And then we have T of 2 equals C plus T of n and T of 1 and T of 1, let us say T of 1 is T of 0 if you like to call it here. T of 1 here. T of 0 equal to some B cost. So if you take all of this and what is it that we are going to see? As long as n is greater than I, T of n equals IC plus T of n minus I. Okay. And if you add all of this, what does this come to be? We'll have T of n greater than I here. We have T of n is equal to how many are there? There are n c plus b. C is a constant, b is a constant. So if this is like T of n is equal to C1n plus d. Therefore, T of n equals order of n. Okay, so you can write recursive functions like this, and I will take more examples in tomorrow's class, and we will stop the lecture for today.